Hey you guys, this is Professor Vitt, and let me introduce you to the module on nature and numbers. Another way to think about this module is it deals with oddities, or things that we think are unusual, with regard to nature and numbers. So we'll talk just briefly about how this is organized. I'm going to talk about nature, then I'm going to talk about probability, and then I'm going to talk about math ignorance. However, this could simply be this could be divided totally differently. This could be nature and math ignorance. But when you get right down to it, it's probably easier to break up the presentation into a couple of smaller parts so we can do some chunk learning, right? Learn in bits and then go on. And so we're going to divide this into nature, probability, and math ignorance. First up is nature. Now, you may want to say, gosh, what do I care about the oddities of nature? Well, you don't have to, but realize this. What we think is normal in nature, or what we think is natural in nature, is no representation of what is normal or natural in nature. Most of our lives, we're living in a confined geographical space. Even if you travel a lot, you're not likely to see some of the more strange and unusual facts about nature. And so it shouldn't come as a surprise to you that occasionally there are things in nature, phenomena in nature, which look very strange to us, if for no other reason than we haven't seen them before. Let me give you an example of this, and I want you to try and tell me what you think happened here in this photo. You can hit pause for a second if you want. You don't have to. But the most common answer is there was some type of predation going on here. So there was a seal and it was attacked by a polar bear, or there was a polar bear and it was attacked by a yeti, or whatever it is, right? But this is obviously the blood of an animal, and quite a bit, right? It turns out, no, this isn't the blood of an animal at all. This is just iron oxide, or some kind of rust anyway, that's seeping up from the earth right here, right? From the terra firma, and it's coming up through the ice and coming out. Now, if you didn't know that, if you didn't understand rust or how this would go, you might think that there was blood here, or you might come up with some very strange ideas to explain little eruptions like that. Now, it doesn't seem like a big deal to us, but I'm going to give a couple more examples to show you that our intuitions about what's normal in nature is not really a very good idea, isn't a very accurate representation of what would be normal in nature. And this matters because if we run across something that seems to be inexplicable or doesn't seem to be natural to us, it doesn't necessarily mean that it isn't natural or it isn't part of nature, right? It just means that it doesn't fit with what our intuitions say about nature. This is a great example. It's blue lava. No, I didn't adjust the saturation in the picture. This is actually blue lava. It has a different compound in the rock, and so when it becomes molten, it becomes blue. Again, it doesn't seem like a big deal, but stop and ask yourself, if somebody would have said, is lava blue? You probably would have said, no, it's not blue, it's red. And so it's just one more example where we don't spend enough time in nature. We haven't examined enough of it generally as individuals to know what's normal or what's not. This is an absolute classic. This is a picture of a mountain, and it has a lenticular cloud on top of it. It's very strange looking. Lenticular clouds have a huge history when it comes to unidentified flying objects. Very often, lenticular clouds only form in certain kinds of conditions, certain types of air pressures and so forth, and humidity or precipitation. And when they do occur, they look very strange. In fact, there are lots of cases, not lots, but there are some, where people claim to have seen something in the sky, and then people have consulted meteorological charts and so forth, and they said, oh, look, the weather conditions would be appropriate for a lenticular cloud. Maybe they were just seeing a lenticular cloud. Now, it's not always the case. Sometimes there are sightings, and people say, oh, this should be a lenticular cloud, but it's not. The weather conditions aren't right. But it's a rarity in nature, and it's not something that you'd normally see. And if you were in an unusual place or something like that, and you saw a lenticular cloud and you were reaching for an explanation, it's quite possible you would not come up with a lenticular cloud. You might have some other fantastic story about what happened. Okay, this is the Moki Marbles, Utah Navajo sandstone, I believe. So these are naturally occurring small bits of rock. You wouldn't think that by looking at them. You might think they needed to be produced by people. Um, Obvious mistake, but it doesn't occur everywhere, right? And so it's just one more example where you want to be careful if you hear some ancient account or some distant account about something miraculous. Remember, your idea of what's normal in nature isn't always going to be the same as what is normal in nature. Oh, one of my classics. Okay, the moving rocks of Death Valley. This one was a stumper for a long time. In fact, I don't think it's technically been solved. If you can see here, this rock is moving slowly, but over time. You can see it kind of moving across the desert floor and leaving this track. Now, there have been all sorts of explanations as to why this is happening. Supernatural ones, definitely. But the best current guess is probably that it gets very cold and maybe there are little teensy ice crystals that are forming when the temperature drops at night. And then the ice expands and it moves the rock just a certain distance, just a very small amount over a great deal of time. And so that explains it. Now, if you didn't know what it was, you wouldn't know what it is. I know I can only show you so many slides and say, look at how weird this is, and it kind of has less of an impact. But one thing I want to stress is, when it comes to nature, we're kind of novices, and we really don't know a lot about. I mean, we know a lot, but we don't know everything about the Earth. In fact, we know just such a small amount of it. Take a peek at this. What do you think it is? So the most popular answer is that this is left from pollution, that this would be just the wheel of a tire, a specialized tire, an industrial tire that sat on the ocean floor. Turns out, no, that's incorrect. This is actually the pattern made by a male pufferfish when it's mating. So if you didn't know what this is and you saw it underground, you might come up with all kinds of theories that this could be left by an alien craft or, who knows, right? But the idea is it's something that you wouldn't normally think was made by a fish, and your intuitions can be very misleading. Okay, these are the Mahjong pipes in China, and when these were first discovered, it was considered they were considered to be literal pipes, that these must have been the relic of a more advanced civilization from long ago. You can almost see this looks like a pipe, right? And the way that they are situated relative to this cave, people had all sorts of ideas about whether or not they had some sort of ceremonial or ritualistic function. It turns out it's bacteria of some kind that grows in this stone in a strange way, and it makes it look like a pipe, but it's not really a pipe. So again, it's another case of something that looks man-made, but it's not natural. Our conclusions are wrong because we don't have enough knowledge, right? And so we're going on our intuition, and our intuitions lead us down the wrong pipe. So all that for the very simple point, nature can be weird. Okay, and our intuitions about nature aren't really a very good guide to what's true in nature. Okay, good. Okay, let's talk about probability for a second. There are 3 errors that we make with regard to probability. I'll cover them each below. But generally speaking, we're really bad judges of probability. We're not good at figuring out what's more likely, A or B. But we're very confident in our assessment of probabilities, usually. So it comes as a surprise to folks that we judge probabilities wrong. So let me give you an example. Let me ask you, just statistically speaking, so by that I mean in terms of numbers of people killed each year, right? What's more likely to kill you? Okay? Do you think sharks kill more people per year or cows do? Okay, turns out it's cows. Cows kill more people every year than sharks do. So if you were thinking you're gonna take your chances with the cow, surprise, it's killed you. Okay. Now, what's more likely to kill you, a snake or a bathtub? Again, we're just speaking in terms of raw numbers here, right? which has more deaths per year, a snake or a bathtub? You guessed it, it's the bathtub, the deadly bathtub. Now, there are sort of wrinkles to this, right? You could ask further questions about the statistics that I'm using here, and you could say, well, wait a minute, I mean, what percentage of snake counters end in death versus what percentage of bath encounters end in death? Fair enough, I get it. We could drill down on the details, but what I use this for, the point of this explanation is to show you the availability bias. And what this is it's when one tends to recall information because it's more readily accessible, and it's more accessible because it's more recent or impressionable or otherwise, not because it's necessarily more accurate. So let me come back to you. I'm going to just throw out a guess that you hear about more shark deaths, or you hear about sharks killing people far more often than you hear about cows killing people. And I'm also going to guess that you hear about people dying from snake bites far more often than you hear people dying from tubs. And that would be correct. And so when I ask your brain, well, what's going to be more dangerous, cows or sharks, snakes or tubs? Your brain's going to go, oh, well, snakes are more available. I mean, this is more obvious to me that snakes are deadly, right? Whereas tubs are kind of fun sometimes, right? It's your brain tricking you. You don't actually know the statistics, right? Which is more deadly, the tub or the snake, right? You don't know, but your brain kind of institutes a shortcut and says, well, snakes seem a little more scary, so let's go for snakes. But in point of fact, that's wrong. And what's happening is your brain's giving you the more available answer, the more readily accessible answer. And so that explains why you have this kind of result. So one way in which this availability bias plays out is that people tend to perceive the world incorrectly on the basis of this bias. And really the reason here is, let me give you a great example of how your worldview can change when you realize the impact of the availability bias. I think the statement on the screen right now is a fairly common sentiment, at least in the world today. You can find it. It's this idea that the worst massacres in the history of the human race have occurred in the 20th century, and that we're just as violent now as we ever have been. And this is cause for great pessimism and distress in people, that it's been thousands of years, and yet have we progressed? Well, it turns out we have. If I were just to ask you, name 20 massacres that have happened in the human race where more than 5 million people have died, you might give me a few, right? World War II, World War I, maybe some famine, Mao Zedong, maybe Genghis Khan. But beyond that, it's a little difficult to reach far back and to come up with them. Well, turns out people keep statistics on this stuff. Necrometrics.net, I believe. I can't remember if it's .com or .org, but people track this stuff. And when you actually look at the statistics to determine when was the most violent time, or are we more violent now than we ever were in the past, the statistics tell you no. In fact, we're remarkably less violent now as a whole, as a species, than we ever were in the past. If you don't believe me, take a look at the 20th deadly events in human history. And if you were to make the equivalent deaths today, what would this be, right? How would this look? Well, Genghis Khan, 13th century, Mideast slave trade, Zin dynasty. The list goes on and on and on. So what does this mean? Why does this matter? It matters because when people think that we're more violent now, or just as violent now as we ever have been in the past, they're not relying on facts. They're relying on what things come to mind. Well, violence, 20th century, you think of World War II, right? And it seems almost like a truism that the worst things that have ever happened in the history of the human race have happened in the 20th century. But when you consider them as portions of the population, it's actually false. And when you look at homicide rates and crime rates, just really very quickly here, this is an alternate list of the worst things that people have ever done to each other. But when you look at historical homicide rates, yes, those things exist, yes, people look at them, you find that violence has declined dramatically over the course of human history. Homicide rates, even as recent as 250 years ago, were 8 times what they are today. So you get these ideas. You ever hear the phrase, cut off your nose to spite your face? That's because people used to cut off each other's noses. This was a thing in medieval times. And it turns out people used to kill each other far more frequently than they do now. Now, you wouldn't think that if you were just relying on the availability bias. So it's just one more way in which you can see that your brain takes shortcuts, right? And those shortcuts don't always work, and they don't always result in true beliefs. So, okay, and so just these are a couple of further instances of the availability bias. This happens a lot when people, this first list here, this is a famous British psychic. She's passed, but when people report meeting a psychic, they'll say something like, oh, you know, the psychic knew my husband's name was Tom. Well, when you look back at the transcript, what that usually means is the psychic said, I'm picking up something with a T, I'm picking up Terry or Tom, and then the person says, oh, the psychic said my name, Tom, just like that. Well, that's because when they say that name, it sticks out. It's like ringing a bell, right? But all of the other names that they've been trying to get in the meantime, Terry, what about Terry? She said Terry. Doesn't that count just as bad as Tom? That's like a 1 out of 2 guessing, right? Those details tend to blend away, and all your brain remembers is, oh, the psychic knew my name. Oh, the psychic knew I was looking for love, right? And all the rest of it washes away because those things are easier to remember because they're so exciting. Okay, so this is just another little point here. With regard to the availability bias, the believability of something is often similar to the ease of recall, meaning things are more believable when you can recall them easier. And so this is just another version of the availability bias. You essentially get distorted by how vivid information is, right? I ask you, gosh, name 20 massacres where more than 5 million people died. The first thing you think of is probably World War II, right? That's so vivid in your mind, but you would never think to access or think about other massacres because they don't come to mind as easily. They're not as historically vibrant as World War II is, right? So you can see the availability bias just gets warped even further when you have this concern with media. This is why it's super important to diversify your media, whatever it is, because if you are constantly saturated with the same perspective, then you kind of take that perspective on. It comes to mind more easily to you, and that distorts your vision. Another example of the availability bias front and center was this craze with strawberry allergies. It turns out strawberry allergies are remarkably uncommon, but there was a media report, and gosh, everybody had strawberry allergies, and it was just because that allergy was pervasive in the media, and so it was easier for people to recall. Okay, now we're going to move on to something a little different. I'm going to read this question out loud, and then I'm going to explain the answer. So here we go. Lupe is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which is more probable? A or B? A, is it more probable that Lupe is a bank teller, or B, Lupe is a bank teller and is active in the feminist movement? Stop and ask yourself, which one of these is more probable, A or B? Your answer should be A. Why? Well, general events will always be more probable than specific ones. And an individual event will always be more probable than the individual event and another event attached to it. So it's more probable that she's a bank teller than it is probable that she's a bank teller and is active in the feminist movement. So think for a second without this prompt, and it'll probably be more clear to you. What is more likely? I get into a car crash, or I get into a car crash while I'm drinking a cup of coffee, right? And maybe a thermos full of coffee. Well, you're going to say, well, that you get into a car crash, right? Because because the second event, the car crash and the coffee, is going to be less probable than the one where you are just driving the car and you get into a car accident. Why? Well, because you're not always drinking coffee when you drive around, and it's a more specific instance, right? Driving with coffee is more specific than just driving generally. And that's all that's going on here with this example with Lupe. But what happens is your brain tricks you. See, you read this stuff, she's single, she's outspoken, she's bright, she majored in philosophy, she's concerned with all this stuff. Okay, I got it there in my head. And then I say, what's more probable? She's a bank teller, or she's a bank teller and is active in the feminist movement. And somebody says, well, I'm going to say active in the feminist movement because, look, it tells me up here that she's concerned with issues of discrimination and race and da-da-da-da. Okay, that's true, but I'm not asking whether B could also be true of Lupe. I'm saying, what's more likely? Well, it's more likely this general condition here, because this is a general condition and something more specific. Does that make sense? It's called the conjunction fallacy. And it's exactly what it sounds like. People treat a specific event as being more probable than a general one. And so that's the conjunction fallacy, because if you look, conjunction just means to bring together. Our two options here, B, I've conjoined Lupe being a bank teller with her also being active in the feminist movement. And I'm saying, well, that seems more probable, right, when you first read the question. Well, no, it's not more probable. It's what's more probable is she's only a bank teller, because that's a general condition. When I attach other stuff, that she's active in the feminist movement, automatically, although that may be true of her in this example, it's not more probable, right? Okay, so that's the conjunction fallacy. All right, next one, illusory optimism. This one, it's called the optimism bias. It might have a greater, more profound evolutionary use. The optimism bias might have kept people going, right? It makes them a little more chipper and happy to meet the day. But let me give you an example of the optimism bias, okay? You've received a full scholarship to attend the university of your choice. So suppose you complete this class, you go on and you do extraordinarily well, and you've received a full scholarship to go wherever you want to go. If you don't place within the top 30% of your class in the second year, you're going to be responsible for the entirety of your tuition, right, for the remainder of your years. Do you attend there? Now, most people, I think, at least when I do this in class, most people say, yeah, I'm going to go for it because I think that I can place within the top 30%. I mean, I got the scholarship, right? Well, the odds are against you on this, right? There's a 70% chance that you're not going to get in the top of the class. And so, if you were betting just on the basis of percentages, you probably wouldn't, right? But when I say that it's you, and this is something that you're going to be able to do, for some reason your brain gets optimistic about your outlook, and it lets you think that this is more likely than it might otherwise have been. Now, I'm not saying this is a bad thing, right? To be optimistic is a good thing, and I would encourage you to be optimistic. But this does have a dark side, and the dark side is people don't always prep for a rainy day. An absolutely classic example of this is life insurance, right? People just assume that they will, that it's just not going to happen to them. They're not going to die in a car crash, right? So they don't necessarily keep their life insurance where they might want to keep it to provide for their family after they're gone. People don't assume they're going to be getting cancer anytime soon, right? They say, no, I'm not going to, But when you look at rates of people who contract cancer, right, they're high enough that chances are pretty good that at some point in your life, right, you would. But in a first-person perspective, you never think that stuff is going to happen to you, right? And that's just what illusory optimism is. And it really affects, like I said, insurance coverage. It does also pop up when people are trying to come up with things that they're going to get done. This happens to me absolutely every day. I say, okay, I've got 6 things I'm going to do. Boom, 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 boom. Now I only get to 2 or 3 of them. Why do I think I can get to all those tasks? Well, my brain is very optimistic and it thinks I'm going to get it done, right? So that's a good example there. Okay, moving on now to our last very last section on math ignorance. So take a deep breath. We're almost through it, and you've done a great job. I mean that. I know it's tough to sit and listen, but you're doing fantastically. Okay, front and center for the math ignorance section is the birthday problem. You might have already heard this birthday problem before. If you have, I apologize. If you haven't, prepare to be amazed. Okay, here's the birthday problem question. What is the minimum number of people you need in a group for it to be more likely than not that two of them have the same birthday? So keep in mind you have 365 days in a year, and I want to know how many people do you need to get in a group to make it more likely than not that two people share a birthday, meaning greater than 50% likelihood. So take a second and think about that. Most of the time people look at the number of days in a year, which is 365. So if I want to make sure that I've got a better than 50% chance of having two people in the room that both have the same birthday, I must have to have half of 356, which would be 178 or something like that, right? So most people's numbers are higher like that, 178. It turns out that the number is 23. The answer is 23. You only need 23 people in a room to make it more likely than not that two people share the same birthday. I do this every semester. I think once I didn't get two people in the same room who had the same birthday, and none of them believed me. But since then, it's remarkable. You can get a room with 20 plus people, and actually I've done pretty good on it. So the answer is 23. You might have thought that the number was much higher, 150 or so, but the answer is 23. By the way, just as I point this out right here, I have a picture of a cake here for the birthday problem. It's from cakerex.com. If you're ever looking for something to do, that's a great, absolutely great website, and I am a Cake Rec reporter. But you can see what has happened here, just a little comedy aside. Somebody wrote what they wanted on the cake on a piece of paper, right? They want 30 with stars and sprinkles around it. Well, somebody literally wrote out 30 with stars and sprinkles around it. Okay, that's just a little joke for you. Okay, so the answer is 23. Where were we? Remember, what's the minimum number of people we need to have in a room to make it more likely than not that two of them have the same birthday? People normally say a really high number, 150 something, but the answer is 23. Gosh, how could we be so off? We are awful. We are awful with exponents. We just have a very, very hard time understanding how they work. It is just extremely tough, right, for our brains, unless we actually do the math. So this is the calculation here, right? The number of people you have, the calculation of uniqueness of a birthday, times the chances of a unique birthday, the chances that a birthday are matched. So if you are interested in mathematics, you can see this here. Now what's going on, you can see in this graph with this exponent, right? You tend to think, well, it's going to have to be, I don't know, maybe something like this, right? Your mind is thinking, well, 150-ish people, here's our probability, so it goes 150 like this. This is what your brain thinks, 150 people, maybe even farther out, right? Because that's 100 people will be over here. But actually, no, the exponents crank up like this. So you take the number of people times the calculation of uniqueness, chances of a unique birthday, chances of the person are matched. At 23 people, you get 50.9%. Now, you may say to me, yeah, don't even get the math. Frankly, don't care. What's the answer? The answer is don't trust your head for math, particularly when it involves exponents. You're not really good at it. And that's because, unless you are, by the way, and I apologize, a mathematician, good for you. But most people, most of the time, this is a genuine surprise. And that's because we just guesstimate, and our guesstimate is totally wrong. So it's another case of innumeracy, where we're not necessarily able to understand the nature of these abstract relations. And so we just kind of wing it. Your brain goes, wing it, we need the calories, wing it. And then it wings it, and it's completely wrong. So what is the point? Why does this matter? What are we doing all this? Look, there are going to be absolutely remarkable coincidences that exist between people. when you consider the number of things that people, the number of traits that they have, the possible number of traits that can be matched, you're going to come up with some very, 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 very remarkable coincidences between people, just as a matter of math, right? Just a matter of logic. People underestimate how probable some of those events are. Let me give you an example. Well, no, I won't do that yet, but I'll do that in a little bit. It talks about coincidences. In fact, this is a good time to just lead into coincidences. So the birthday problem, there are going to be remarkable coincidences between people, and don't trust your head when it comes to estimating exponents. Okay, so now, moving forward here with our math ignorance, we are going to talk about coincidences, randomness, and large numbers. First up, coincidences. I hope you can see that picture. It's not drowned out by the title, but you can see a bunny and a pud, and they are both black and white. Just a coincidence. Okay. Generally speaking, we tend to notice coincidences, and we treat coincidences as being highly improbable. In fact, we have a name for this called synchronicity, and that's typically a name that people give to coincidences that occur when they think that there's something else to it, right? Oh, what a coincidence. It wasn't a coincidence, it was synchronicity. In other words, there's some greater order of fate at work here. This couldn't be a coincidence. It had to be. It's so unlikely that this actually must have been designed or part of some kind of fate. People will often compare traits of Abraham Lincoln to traits of John F. Kennedy. Now, I'm going to give you a little reader here of them. Lincoln is elected in 1860, Kennedy in 1960. Both were deeply involved in civil rights issues for African Americans. Both were assassinated on a Friday in the presence of their wives. Each wife lost a son while living at the White House. Both men were killed by a bullet entering the head from behind. Lincoln was killed in Ford's theater. Kennedy was killed in a Lincoln convertible made by Ford Motor Company. Both men were succeeded by vice presidents named Johnson, who were Southern Democrats and former senators. Andrew Johnson was born in 1808. Lyndon Johnson was born in 1908. Is it getting weird enough for you yet? The first name of Lincoln's private secretary was John. The last name of Kennedy's private secretary was Lincoln. John Wilkes Booth was born in 1839. He was the person who assassinated Lincoln. Lee Harvey Oswald, the person who assassinated JFK, was born in 1939. Both assassins were Southerners who held extremist views. Both assassins were murdered before they could be brought to trial. Booth shot Lincoln in a theater and fled to a barn. Oswald shot Kennedy from a warehouse and fled to a theater. Lincoln and Kennedy each have 7 letters. Andrew Johnson and Lyndon Johnson each has 13 letters. John Wilkes Booth and Lee Harvey Oswald each have 15 letters. So, it looks like there are all of these bizarre and strange coincidences that exist between these two people. How would you explain it? Well, there's more, right? It just goes on and on and on and on and on. And you can do this with almost any 2 events that you can imagine. Look for this on the exam, right? Where somebody's talking about the Hindenburg or 9/11 or something. And people are so quick to point out some of these remarkable coincidences that exist between events. But it turns out that this notion of coincidence is pretty specious. It's kind of paper thin. The reason why these coincidences seem so remarkable to us is because we are completely ignoring all of the other cases where these people aren't similar, right? Look at Lincoln was elected in 1860 and Kennedy was in 1960. Suppose both of those are true. That's not really a big coincidence. You know, you could look at, sure, maybe that was the same year, but did they carry the same states? Did they carry the same precincts? Did you have the same structure of states, right, at this time? Both were deeply involved in civil rights for African Americans, but in dramatically different ways, right? I mean, this is a huge generalization, and when you look at the course of their political careers, they were very different people. Both assassinated on a Friday in the presence of their wives. That's about the end of the similarities there, right? having looked a little bit at the Kennedy assassination, what I know about the Lincoln assassination, these were different crimes. They occurred in different places, at different times of day, by different people. The only reason that this stuff looks amazing is because we're looking at only the similarities. They're different height, they're different weight, they had different accents, they had different numbers of teeth, right? All this stuff is different. But when I put all the similarities together, it looks like, oh my gosh, that's great. But it only looks that way because you are focused in on the similarities. You let that become the impression that you have, and then beyond that, it doesn't seem very remarkable. So remember, these coincidences may seem remarkable, but they're not when we take into account all of the other things that these people don't have in common. Let me give you an example of a coincidence just from my own life. This is short. I used to live in New York City, and when I was there, I went to a party. It was a fairly posh party. I was a grad student. I wasn't a posh person. And I got to talking to someone there, and it turns out within a minute, he said, oh, who are you, blah, blah, blah. We started chatting, friend of a friend. Within a minute, we had come to the realization that he knew my hometown of Redlands, California. Now, I was thousands of miles away from, well, hundreds at least, miles away from California. I mean, thousands. And yet, I went to this random party, and of all the people in this party, this person knew my hometown because his grandmother's family had built a big home there. There were, and to his grandmother's dying day, she spoke of Redlands so fondly, and she loved it, and she talked about the yellow house, and da-da-da-da. And as we started talking, I said, well, where, so your grandmother's family lived there? Where was the house? And he told me, oh, Judson, and, blah, blah, blah. And I've been to that house. I have seen your grandmother's house. It's beautiful. And he's like, really? And right, of 14 million people in the greater New York area, I ran into the one person whose grandmother's house I'd been in. Well, look, if I would have talked to other people at that party, there would have been other remarkable coincidences. So it's just because there are so many traits and so many things that people could have in common. When you hook on a few of them, it seems remarkable because you're only looking at the hits. You're not counting all the misses that fall to the wayside. Okay, we are on to randomness, you guys. Let's talk about randomness. Okay. So, a good way to start thinking about randomness as a critical thinker is to look at an argument that's very famous in philosophy. It's a design type of argument. It's an attempt to prove the existence of a designer for the universe based on how improbable the arrangement of the planets and the stars and the conditions thereof are. So if the universe, the story goes like this, right? If the universe had just been a little different, only slighter, then life would not have been possible. If you take all of the cosmological constants and you arrange them across the United States, right? If you put all of the values that they could have been at, and you, right? So you have we'll just go crazy. We'll say a nice round number. Let's say all of the values available to different cosmological constants stretch 5,000 miles. So, right, all the values that you could have for the initial conditions for the universe. So these are things like gravitational constant and stuff like that. If those had only just been a skosh different, then none of this would have been here, right? Think about it this way. The Earth is in a Goldilocks zone, right? It's not too hot that the organisms burn up, and it's not too cold that the organisms freeze. It's just right. And so we've all developed in this area where it's just right. If we didn't have, I believe it's Uranus, sucking in all of these bad asteroids, the Earth would have been plummeted, right, with asteroids. If the planets had been arranged even just marginally different, life wouldn't have been evolved. And when you look at all of these things, right, think about the asteroid impact that kills all the dinosaurs, right? If that hadn't happened, or it would have hit differently, humans might not have been here at all. And when you look at all of these remarkably improbable events that have occurred in the past, it's very difficult to say, yeah, we were just going to show up. Instead, it looks like it's so improbable that someone was there kind of helping, right, to sort of fine-tune the universe and to make it so that we could live in a meaningful and peaceful way here. This is an extremely intuitive and very, very compelling argument, okay? It just is. But it's based on a misunderstanding. It's based on a mistake. It's based on the lottery fallacy, okay? And so let me explain how this works. This is Solomon Jackson in possession of $259,900,000. Good for him. What are the odds of Solomon winning the lottery? And I mean this particular individual, right? I mean, the odds have to be in the hundreds of millions. Of all of the people in the world who could have won the lottery, boom, it was Solomon. What are the odds? It had to be fate, right? This just is the lottery fallacy, right? X must be designed because X is improbable. But when you, the way to think about the lottery fallacy is that it's actually asking the wrong question. The lottery fallacy is asking you, what are the odds that this particular individual person right here is going to win the lottery? Well, 1,000,000 to 1. Okay. But that's different than saying, what are the odds of anyone winning the lottery? Right? So here's a variation. Suppose we're walking on the beach. And you see I see some sand on the ground, and I pick up, yeah, that's right, that's a hand. I pick up a little 1 grain of sand off of the shoreline, and I hold it to you, and I say, can you imagine, out of all of the grains of sand in the world, trillions of grains of sand, I picked up this one? What are the odds of that? 1 in, quadrillion? I don't even know. They're astronomically high. It must have been predestined. It must have been fate that I picked up this piece of sand because it's so improbable. Well, you would tell me, Professor Vitt, are you sniffing glue? We're walking on a beach and you tell me you're going to pick up a grain of sand. The odds of you picking up a grain of sand are very good. Now, the odds of you picking any one particular piece of sand are very remote. Those are two different questions. And so when you say, oh my gosh, what are the odds that Solomon won? Well, they're slim, but the odds that somebody will win is pretty good. And it just so happened this time it was Solomon. Okay, so the way to think about this is then when we talk about, gosh, it seems so improbable that life evolved, we say, well, sure. I mean, it does seem really improbable. But, and this is the big thing, what is the likelihood that some form of life would evolve? Well, probably pretty good if we're just looking at the history of the Earth, right? There have been literally billions of species, I'm assuming billions, millions of species of life that have evolved on this planet. We're just one of them, right? So the odds of a species evolving on a planet with our lives like this, or with conditions like this, are pretty good. But that doesn't then mean that we can infer that our own evolution was so improbable we can infer design. Okay, if that doesn't make sense, don't worry about it. We just have the lottery fallacy. You'll see its application in the quiz, mostly having to do with people winning the lottery, and maybe they pick a specific number of to win, right? And they say, gosh, what are the odds? So those are the conditions under which you'll see it. Okay, now we're going to talk about randomness a little bit. I just want to show a tick of a clip here, if it's going to let me. Nay, it won't do it. Okay, we're going to talk about World War II and randomness. Now, what you're looking at here in figure 2.2 is the points of impact for the 67 V1 rockets that were dropped in central London. And when people were living through this god-awful event, they noticed a kind of a distribution to the V1s. You look over here, there's a cluster around Regent's Park and a cluster over here in the River Thames, but these other regions seem kind of open. And on the basis of where these bombs were landing, the British were saying, Well, the Germans are targeting, right? They're targeting over here by the Thames, and they're targeting this area, the Regent's Park. Um, it turns out this is false. We know this conclusively because we know a lot about those V1 rockets because we know the scientists who built them. And the V1 bombs didn't have the capacity to target with that level of precision. They just couldn't. The Germans could shoot a bomb over there and say, okay, hopefully it makes it to London somewhere, and more or less it would make it. But they couldn't pinpoint where they wanted it to land. But people looked at this distribution and they saw a pattern because it didn't seem random to them. And this is the part about randomness that's hard to understand. Randomness can be clumpy. Randomness can be uneven. This is a uniform distribution of dots throughout a square. This is a clumped distribution of dots throughout a square. And this is a random distribution of dots throughout a square. Now, if you look long enough at this, you might try to generate some kind of pattern, right? But there's no reason to do that. It's just that when we have these random results, they'll be clumpy. Look at these two sequences of heads and tails. They don't look random, right? It doesn't look like you could randomly have 3 heads and then a tail and then 2. It just seems weird. Well, in fact, these absolutely are random tosses of heads and tails. They just don't look that way to us because we somehow think it's supposed to be evenly distributed, right? It doesn't. This leads to 2 fallacies that exist in sports. One of them is NBA players will often say during a game, if they make a few baskets, they'll say, hey, I've got a hot hand, give me the ball, right? Because I couldn't just be randomly getting these things, right? I'm hot, right? And it turns out, no, there is not such a thing as having a hot hand, that people, when they're shooting the ball like that, they're not more likely, they're suddenly not incapable of missing. They're always shooting at or about their average. It's just that when you look at the larger samples of data, you see that that although they might have strings where they hit a bunch of baskets in a row, overall, when you look at their statistics over the course of several games, they're fine. It evens out. It develops into an average. So there isn't really such a thing as a hot hand. If you want to learn more about this, I would look in a great book called Why We Believe It Ain't So. And you can email me. I'll give you the title and the bibliography. But they actually went to the Philadelphia 76ers because the 76ers actually tracked data finely enough to try to determine whether or not there was a hot hand, and there isn't. Sometimes you see this when people talk about players in Major League Baseball having clutch hitting, that there might be players who are just very extraordinary, and when the situation is dire, they're able to elevate their game and be more successful in those circumstances, perform above their average in a way that they couldn't in others. And it turns out, no, that's false too. There's been a lot of statistical analysis on this in baseball because there's so much data in baseball because it's been played for over 100 years at a minimum. So our inability to understand that randomness can be clumpy leads us to generate or believe in these false things like the hot hand or clutch hitting. So just be on the lookout, right? Randomness does not always look random to us, and sometimes we think there's more going on behind the scenes as a result. Okay, large numbers. Let's do this thing. Large numbers. Okay, this is a bit of a surprise to you guys, but we're not good at estimating large numbers either. We're not very good at it. Okay, so in order to talk about large numbers and how we're not good at estimating them, we're going to talk about death premonitions. Now, what I mean by this is that, maybe you have thought about somebody, and while you're thinking about them, you find out later, I was just randomly thinking about Alex, and then I found out Alex died, right, that day or that week or that, right? If this has ever happened to you, it is it can be anyway, profoundly unsettling, right? This happened to me family that we'd grown up with, and the father with whom I was not my father, but the family's father. I was fairly close with him. I was working in an industrial bank, typing away, and I just randomly started to think about Alex. And I remember looking at the clock and thinking, well, that's strange, but I had such a sense of him at that moment. And, this isn't unnatural. I mean, you randomly have memories come into your head throughout the day from different parts of your life, and that's what happened to me. And then I got a call later in the week from my mother, and she said, Rob, I hate to tell you this, but on Tuesday, Alex died. And I said, he died? Oh my gosh, when? Well, it was like within that hour he died, I was thinking about him, and I just thought, whoa, right? Very unsettling. I mean, it's very strange, right? And so when people have this experience, they naturally think, well, maybe I was picking them up, right? Maybe I was picking up some vibration or energy or something from this person. And I mean, I know firsthand, having been through this, it really is a remarkable event, and I can see how natural that kind of inference would be. But Smith helps us walk through some math here with regard to death premonitions. The idea is this. I'm going to give you the basic idea, and I'll show the calculations on the screen, but we're not going to get out our pencils and paper, right? The general idea is there are so many minutes, there's so much time in a year, and there are so many people that you know, and so many people that you know every year will die, that eventually you get a number, right? All other things being equal, the odds of thinking of somebody while they're dying are 1 in, 105,000 or whatever it is, right? And then you take that very small number for you, and then you multiply it by 300 million people, and you're going to get, even in a very improbable case, right, you're going to get people to whom this happens. So here's how it goes. So suppose 10 people who are going to die in a year. It's a round number, you can Google it. And suppose that we divide up the year into 5-minute intervals. So any person on the list of 10 who are going to die in the year, right? The odds are 1 out of 105,102 that you thought of them for 5 minutes, right? Now, for these 10 doomed people, the chances go up to 10 out of 105,000. So the odds end up being about 1 in 10,000 that you're going to think of a doomed person before they die. Okay, so pretty slim odds, right? 1 in 10,000, not likely to happen. But if you had 10,000 people, you would have at least one instance, right? Now suppose you have 300 million people. We have more than that in the US, right? Well, now suddenly you're going to have 25,000 people for whom these death thoughts, right, these death premonitions just come true by chance. That's 70 people a day to whom this happens just by random chance in the United States, according to this calculation. So you can see how when you're dealing with numbers that are very, very large, it is hard for your brain to understand, because I'm just this one person, right? And I'm thinking of this one other person that I know. But you're not just the one person. There are hundreds of millions of other people, all of whom are thinking about people themselves. And when you get the numbers to be very large like that, even with very improbable events, you're going to get some miraculously improbable thoughts or events to happen in that period of time, right? This happens often with people's dreams, right? You have a dream of something, and then the next day it happens. This happens often with my wife, right? Well, our wonderful book author comes up with, suppose you have 250 dreams a night, you multiply, you can see how this goes, right? All of us dream every night. You have 300 million people dreaming every night of other people. Eventually, somebody's going to have a dream of somebody, and the person they had the dream of, maybe something bad is going to happen to them the next day, right? So when you're dealing with large numbers, these things aren't probable. They're almost inevitable. But when it happens to you, it's very unsettling, right? So this goes on and on there. Another way that you can think about this, and this is Smith, it's not really something you're going to be tested on, but he has something he calls Littlewood's Law of Miracles. And the idea is that you could expect a miracle. By a miracle, you mean 1 in a million. You could expect that to happen every month, right? So you experience one event every second, then you just run the math, right? So it's just a way to point out, look, when you're dealing with large numbers of instances, even very improbable events are going to happen because you have such a large number of instances that the probability applies to. Okay, we are on to the final portion of this presentation, and it's fantastic. It's science, and what science has to do with randomness and numbers. So let's crank into this, get you guys out of here, okay? Science is very aware of trying to rule out errors, and one way that we try to rule out chance conclusions is by having results replicated and having sufficiently large sample sizes for our experiments. Let me give you an example. Suppose I conduct some experiment and I'm sitting in Long Beach and oh my gosh, it works, right? I pour the red into the blue and it becomes, I don't know, a nuclear power plant. Some event happens, right? And I say, okay, I've done this. This is amazing. I publish my research, and somebody in Maryland decides they're going to try to do the same experiment. And they do the same experiment, and oh my gosh, it doesn't work, right? And this happens across the country. And finally, this happens to 99 other researchers in the country, but only one of them replicates my results. Well, that might tell you something about the likelihood or the strength of my conclusion, right? Okay, so just a last point about science, super brief. Science is built on replication, meaning someone else copying my results, right? If I'm doing an experiment, it's very important that people throughout the world, if I have discovered something in an experiment, that people are able to replicate my results. The reason why is the more you can replicate the results, the more you show, well, this isn't just something that happened randomly, this is a significant result. And so that's what science tries to do to control the demon of randomness, right? We try to allow, well, it wasn't just a one-off event. People have been able to replicate this result throughout the United States. Similarly, we try to fight the randomness of chance by making sure that when we conduct an experiment, we have a sufficiently large sample size. This is related to a point with control groups. I mean, the reason why you don't give the medicine to everyone in a clinical trial is because some people may randomly get better, right? And you need to be able to isolate the effects of randomness from the effects of the variable that you're testing. So that's why we do control groups. We're trying to roll out chance conclusions, right? So those are the 2 points on science. I mean, scientists are aware of this stuff, and they try to counteract the detrimental effects of chance on experimentation. Okay, you guys, I hope that is, well, let's not do that. Yeah. Okay, you guys, I hope that's been helpful. I know that this was a longer video, but it's the only one you've got for this module. So I hope this is helpful just to show you how weird and bizarre nature is. This is actually a dust mite that's been blown up, many-fold. And it looks absolutely scary. So it just goes to show you, right? Nature is a little bit weird, and sometimes it's creepy. Okay, you guys, great job on finishing this. If you have any questions, please don't hesitate to email me. Happy to answer them for you. Okay, thanks a lot, you guys. Good luck on the quiz.